Welcome everyone! In this video, I want to deep dive into an interesting technique for function hooking. You might already be familiar with LD preload trick from the Linux world. We could include custom code in a library and use LD preload environment variable to force our library to take priority and get loaded by other applications. Very useful trick, make sure to check it out. There is a similar trick for macOS too, which I'll cover in another video. I'll post the link in the description if you want to check that out. It's possible to basically do the same thing in Windows using a mechanism called app-init DLLs, very well known to red teamers for sure. For this, I've created a simple script that sets up the required Windows registry keys for us. Let's check this out. Next, I have the code for a DLL library, which in the DLL main function will display a message when it's being attached to a process. Above, I have another function that performs some checks on the name of the current process. We'll use it to decide which processes we want to inject our code into. As it is now, we will only inject into calculator process and the name of the binary is calc.exe. This is a practical check because we really don't want all our processes to be injected. This is a proof of concept, so feel free to expand on this. A side note here, this technique based on app-init DLLs works and can be used to inject code by forcing a library load in almost all Windows processes. There is a small caveat though, which we'll talk about later. You can learn more about the different switch values in the DLL main function by consulting the MSDN documentation. We're only interested in the process attach case here. To decide whether to inject or not, we first extract the full path of the application binary. From there, tokenize it and extract just the name. Then compare it with a hard-coded value, calc.exe in this case. To compile the library, I'm using the CLI interface from Visual Studio 2019 Community Edition. You have the command here for convenience. Okay, after we compile the DLL, we need to modify a few keys in the Windows registry. Let's get back to the script we've seen before. First, we need to enable this mechanism by adding the load app-init DLLs key, and then we need to specify the library we want to be loaded. I'm specifying the library we just compiled in the app-init DLLs key. Notice we could have specified more than one library here. Neat! Another interesting option, whose name is self-explanatory, is require signed app-init DLLs. We will disable the requirement for DLLs to be signed because this is a proof of POC, proof of concept, and mostly because in real life it's very easy to sign a malicious library. Now, just to run this registry script, simply double click on it and ignore the warning because we know that this what the script does. Let's check if the changes have been successfully applied. I have added the registry location to favorites to reach it quickly. All three settings we've added or modified should be here. Let's first launch a process different than calculator. We still expect the library to be loaded, but the process will not be injected with any more code. Remember the should execute function. Based on the source code, only the first message box was executed, as expected, because the name check failed. So the library injection worked fine for cl.exe binary, which is a command line app. What about GUI apps? Let's check with PEView, for example. We get the first message that the library was attached, then another message with the process name from the shouldExecute function. Perfect. Let's try now with the calculator app, which spawns calc.exe binary. We're expecting the library to enter the interesting process branch. Let's see. So what's happening here? Calculator has not been injected. The name of the binary definitely matches our code. You might have noticed that now we didn't even get the first message box. The mechanism worked for some processes, both GUI and CLI, but not for the Windows calculator. Why? Let's see. The library we just compiled is actually a 32-bit DLL, while calculator app is 64-bit. On top of this, we also need to tweak a bit our initial registry script. The name of the registry key is very similar, and the values we need to add or change are the same. Have a look at the difference. We can also verify in CSF Explorer that the GUI app we've used before, PEView, is actually 32-bit and not 64-bit. That's why library injection worked the first time. So let's recompile the code into a 64-bit library. For this, I'll use also the command line CL compiler, but this time I'll load the toolchain for 64-bit. The compilation command line is exactly the same. Let's just change the name of the output library to differentiate between the 32 and 64-bit versions. Should compile without any problems. Next, modify slightly the registry script to reflect the correct library names and execute it to get the settings applied. That's all there is. Before running calculator, let's quickly check in the Windows registry that both the paths have been set up correctly. One is for the current architecture, 64-bit, and the other one for 32. Awesome! We're ready to try the 64-bit calculator. Remember, we're expecting a few message boxes, the last one being for an interesting process. Let's see. Great! Our code has executed correctly, and the calculator process has been identified and the expected code branch taken. A very simple but at the same time very effective persistence technique. Stay tuned for the next videos, when we're going to dig into a custom application, do some function hooking, and also learn cool stuff about OS internals. Thank you very much for watching, and see you in the next videos. Cheers!